Okay, so let's make sure it's taping. Yes. All right, good. So we talked about what logarithms were in the previous section and how to compute with them. Now what I want to do is look more formally at the log function, right? So for example, just like what we did with exponential functions, let's start with just a basic log base 2 x graph function. We know that what this means, if I give you a value of x, right, the log base 2 of that value is the exponent you'd raise 2 to get that input, right? And so let's actually put some values in here. I'm going to put like 1/8, 1/4, 1/2, 1, 2, 4, and 8 in, just for samples, because those are easy values that are powers of 2 that you can actually compute the logs of. All right, so if I put 1/8 in for x, we know that 2 to the minus 3 is equal to 1/8, right? Remember that negative exponent simply takes the power of 2 down below. And so you have a point that's way down here on the graph. And then as you move forward, if I put a fourth in for x, 2 to the minus 2 is equal to 4. And so we have a value right here at 1/4. At 1/2, 2 to the minus 1 is equal to 1/2. So we're at this point. Note that if I put a 1 in there, we saw this before, the only number you can raise 2 to get 1 is 0. And so it crosses the x-axis at that point. And then going forward, these numbers are getting larger. All right, and so a couple of things to note. As the input gets larger, the exponent gets larger. Okay, so the function's increasing everywhere. I can't put 0 in for x because there's no way I can raise a positive number 2 to any exponent and get 0 out. And so we know that 0 is not a tenable input for log. And furthermore, you can't have any negative inputs because there's no way I can raise a positive number to any exponent and get a negative output. That's just not going to happen. And so the domain of a log function, just log base 2 of x, is all positive real numbers. The range is every conceivable real number, right? The smaller I get, the closer I get here with x values to 0, the more negative they become. And the larger the input, the larger the exponent, right? And so it's going to sweep through the whole real line as a range. All right, so I make these observations here. And so just some general properties. I didn't have to choose log base 2, right? If we had done log base 3, just for some sample points, I would have chosen powers of 3 over here, so I can easily compute the logs. And you note that you'd get basically a very similar graph. It might take it longer to get to certain values, right, depending on the base, but all the general log graphs look the same. All right, so here are some general properties of log graphs. The domain is all positive real values, and the general shape is the same, like I'm saying here, and the vertical asymptote is x equal to 0. Remember, it dips down close to the y-axis as x gets close to 0 from the right-hand side, and so that line is in fact a vertical asymptote for the graph of log base 2 of x, or log base b of x, as long as b is bigger than 1. Okay, so this is just a notational thing, right? So when people think of logs, this is a function, right? So the x is an input. Typically, we would write the parentheses around the input, right? That would be more kind of standard notation. But to avoid cumbersome writing, people often just suppress those parentheses. But that does not mean that I'm multiplying these quantities, right? Log base b by itself here without the x is meaningless, right? So you're not multiplying log base b times x, you're taking this function log base b of an input. All right, so just be careful with the notation here. Whenever I have, if the expression I'm taking a log of involves more than just one variable, I'll put parentheses around it, right? So I won't write this, right? This would not mean this. I would have to put parentheses around that to make sure that I take the log of the whole thing. Otherwise, it's just the log of the term that is right next to the log before any plus or minus sign occurs. All right, so just be careful with the notation. All right, for this example, what I want to do is find the domain, the range, and the asymptotes, and then use our reflection and translation properties to graph these using just the ln of x graph, right? So what ln of x is, remember, it's log base e. And so e is about 2.718. The graph is going to look very similar to this, maybe off just a little bit because the number is a little bit bigger than 2, the bases. But still, general shape is going to look basically the same. All right, so starting with that graph, let's see how we get these guys. All right, so for the first one, you want to make sure that the input of the log is positive, right? And so for the domain, the set of inputs, I'm going to require that x minus 3, that input, be positive. But remember, if you want to solve that for x, just add the 3 to both sides. So x has to be larger than 3. And so the domain is everything from 3 to infinity, not including 3. I mean, you cannot take the log of 0 because there's no way to get the base to a number to give you a 0 output. The range is always all reals, right? So that's not going to change even if we're moving them up, down, left, or right. If the range of the original graph, ln of x, is all reals, then all of these translations and reflections have the same range. And we know that the asymptote is vertical, and it's equal to x equal to the value that makes that equal to 0, which is 3. To get the graph of that guy, I'm subtracting 3 from the input, and so I'm going to move the graph of ln of x 3 units to the right. And so I get this general shape. Okay. Compare that to part 2. Here I do not have parentheses around the x minus 3, and so this is ln of x and then minus 3. So you're subtracting 3 from the log of x, not taking the log of x minus 3. All right, so the domain is just whatever you can put in here to make it positive, namely open 0 to infinity. Range is still r, but this minus 3 now doesn't shift to the right. It's going to shift ln of x down 3 units. And so we get this graph. Okay, I'm going to let you read the others here. I want to look at number 6, right, because it contains a bunch of things. So let's hop down to 6. Right? And so remember 6 was 4 minus ln of x plus 2. And so the input of the log has to be positive. And so let me just copy this down just so we can actually see it. It's frozen now. Okay. And so here, let's see, it's still kind of frozen, I think. The input of the log has to be positive. So the x plus 2 is bigger than 0. And so the vertical asymptote is x equals minus 2. Then to get the graph, you're going to start with the input. So you have 4 minus ln of x plus 2. So I'm going to shift the graph 2 units to the left. Then I'm going to apply the minus sign and reflect that over the x-axis. And then I'm going to apply the plus 4 and shift that guy up 4 units. And so you have a movement to the right, a flip, and then you move it up. Okay. All right. Okay, so give these a go. Give these a try and see what you can get. It's the same sort of idea, only now we're starting with log base 4 instead of ln. But again, they all look basically the same. So you're going to use your translation results and reflection results to graph them. Whatever x value makes the input of the log equal to 0 is your vertical asymptote. And then the range is always all reals because it was for the original function. Right, and the domain is all the x values that make the inside positive. All right, so give that a go, and then I'll slow down so you can actually check your results. But these are all at the end of the PDF section 4.3. But I'll actually just go through it slowly so you can pause and check your results. Okay, so now let's actually look at this. We want to actually compare the graphs of 2 to the x and ln base 2 of x, right? What we have seen so far is that they seem to undo each other, right? And that we saw that with the equations. If you take log base 2 of 2 to something, you just get that something back, right? Likewise, if I take 2 to the log base 2 of something, I'm just going to get that something back as well. They seem to be inverses of each other. And so indeed, if you were to graph them on the same set of axes, what you'll get is a reflection over the y equals x line. So you should go ahead and try that just on your graphing calculator or an online one, just to convince yourself. But these guys are in fact inverses. That's how they're defined in some sense. All right, and so we have these sort of properties that if I take a number a to the log base that same number of x, the a and the log base a cancel. And same way here, if I take log base a of a to something, I just get that something back. All right. The thing is, you have to make sure that the base a and the log base are exactly the same, right? So for instance, I can't claim that 3 to the x and log base 7 of x are inverses. They're very close to being inverses, but they're not identical, right? And so you have to make sure that you're applying the log with the same base to get rid of an exponential and vice versa. All right, so go ahead and try these. Again, all this was a formalization of what the log is in terms of a function of x. So go ahead and try to just compute or work through these few problems. There aren't that many of them, just to get a feel for what the graphs of log looks like, the domains and whatnot, and then let me know how it goes. Okay, bye. See you, everybody.